introduction. It's Yawar and student at IIT Kanpur. This is the week one of action session series, and I am the TA for this session. So the course instructors are Professor Hitesh Shrimali uh, and Professor Kushal Kesha, and the course is NOC24 EE-28. Yeah, let's go through its and guidelines. Have any can either in the chat window, raise your hand. Sure you have your microphones intend to speak. Uh, let's make this session an interactive one. So I'll appreciate your cooperation for the same. You may keep a pen and paper handy along with smartphone. Uh, recording link for this session and the lecture notes will be shared by the NPTEL team. Now coming to the prerequisites, I hope you all have gone through the last week's lectures that covered the following topics: uh, mathematical preliminaries, the natural number, rational number, real number, complex number, and polynomial functions, covered under this heading of mathematical preliminary. And I hope you all have already attempted the assignment one. Now, before attempting problems, let's briefly recap what we have learned. So let's start with this circular and hyperbolic trigonometric functions. Uh, we know these trigonometric functions and they can be defined using those well-known ratios of a right angle triangle. We all are aware of that. And we also can define them using a circle. Okay, let me spin. Okay. If ABC is a right angle triangle, then we know that uh, sine of theta is this BC divided by the hypotenuse, and cos of theta is defined as this base of hypotenuse, and then tan of theta is given by the ratio of the two, BC by AB. Now, alternate definition for these sine theta, cos theta, uh, in terms of, I mean to say, a geometrical interpretation for the same can be visualized as follows. The equation for the circle is x square plus y square is equals to 1, right? And we all know basic trigonometric identity, sine square theta plus square theta is sine square theta is 1, right? So can be seen that cos theta and sine theta readily satisfy the equation of the circle, right? So we can say that the points cos theta, sine theta, they form a circle. I mean, they so These points, sine theta, cos theta, they form a circle with a unit radius, right? And uh, an analogous picture of these hyperbolic trigonometric functions exists, and that is this cos hyperbolic function and sine hyperbolic functions. They trace out a unit hyperbola, right? In other words, this cos h of t and sine of t, they satisfy the equation of this hyperbola, unit hyperbola. X square minus y square is equals to 1. Okay, sure if this video won't. Okay, let's do one thing. We'll revisit this later. Actually, my pen is not working for some reasons. So we'll skip with that part. I have this in my presentation itself. So let's revise these first. So the unit step function u of defined as u of t, and it's 1 for t greater or equal to 0, and this function is 0 elsewhere. Okay, so this is also known as the heavy side step function, and alternative definitions of this value exactly at 0 are like half, but you can just ignore this for now. The unit ramp, that is defined as r of t equal to t for t greater or equal to 0, and it's 0 for t less than 0. Okay, so can readily see that we can write this r of t as t times u of t. It's not okay. It's working now. So right, saying is can write this r of t as t times u of t. Is everyone able to see that? Okay, I'll assume that's a yes. So t can be written as t times u of t. So here I have written that can write this r of t as the integral of unit step. So intuitively, uh, it seems pretty obvious, but let's go through a mathematical proof. Okay, so we say that r of t is minus infinity to t u of tau d tau. We can break this of t by definition is 0 from minus infinity to 0, right? And it's 1 from 0 to t. So since it's a piecewise function, we can break this integral into two parts. Minus infinity to 0, it's right first u of t. this one is 0 and this one is 1, right? For positive instances of time, we'll assume t is greater than 0, then this is 1, theta, which is nothing but integral 1 for the interval 0 to t is t, right? And since this t was from 0 onwards, it was 0 for t less than 0, then write it as t times u of t. Okay, that is how it comes about. Let's now go delta function. Delta function or impulse is an idealization of signal, right? Such that it is a signal that is very large, near e equals to 0, and it is very small. I mean, it's span over a small range around t equal to 0. The integral of delta function is 1. So this is how delta function is defined, right? It doesn't matter what is the shape of this delta function, as is shown in this figure. If you assume this epsilon to be a very small number, then whether this shape be a rectangle, triangle, it hardly matters. The only thing that matters is this should span over a very small distance epsilon, and its value, the integral value should be 1, right? And obviously this magnitude will be large. Now, uh, can uh, you all see why this figure shows, I mean, it occurs for an epsilon units, right? This delta signal occurs for epsilon duration, and second figure, it occurs for 2 epsilon duration, right? Uh, as we defined, this integral should be 1, right? So other way to interpret this integral is that this area under the curve should be 1. And for rectangle, area is given by this height into width. So epsilon times 1 by epsilon is 1. And similarly for triangle, area is given by half of base times the height, that is 1 cases. Okay, so this is how delta function is defined, and for the plots, this delta is shown as a solid arrow. Okay, this is how delta function is denoted. Okay, so suppose we had delta t minus 1, then it wouldn't have occurred at t equal to 0, right? This t equal to 0 for the definition was this argument of delta function should have been 0, right? So in this case, if I had to, you know, use that definition for this delta t minus 1, so this t minus 1 have been 0. That is, would have occurred only at t equal to 1. Okay. This is how function would, it would have occurred at confusion. I hope you got the point, right? So yeah, you all to attempt this question before we, if u of t is continuous time unit step function, then this minus infinity to t dt and dut by dt, d by dt of this ut are which functions respectively, right? You can type in the chat A for option A, option B, and so on. Okay, I had couple of responses, option D, and yeah, that is the right one. Since u of t is a unit step function, its integral would a ramp function. We saw this just before, right? This can have a look at this one, right? We want to why it makes sense, right? So a ramp function is the integral of unit step function. And similarly, this delta function is mathematically, if we differentiate this unit step function, we get this delta function. Okay, can actually try that out. Mathematically, that makes sense. Okay, okay. Let's go through some properties of this delta function. The first one is this integral minus infinity to delta of x dx is 1, which comes from definition, right? We find this delta function few moments before like this. Now, second property is that this minus infinity to infinity delta of x minus say f of x dx is f of a. So this what this delta function is doing is that it's picking the value of this function at x equal to a, right? This function would have existed throughout this, and I've stated that minus infinity to infinity delta of x minus a f of x dx is f of a. I want you all to attempt this mathematically. I'll wait for 3 minutes. let's see how we prove this property. Okay, now the argument that we can give for this property is this. We know that this delta function of x, this is 0 everywhere except at x equal to, okay, 0. And if this delta of x had been, if this delta of x would have delta of x minus a, this would have been 0 everywhere except x equal to a. Okay, so now if that is the case, then this integrand, this minus infinity to infinity x of delta of x minus a f of x dx would be 0 for all x except at x equal to a, right? So this integrand is 0 everywhere and only distribution x will be x equal to a. Okay, so if that is the case, then we can readily replace this f of x by f of a, right? Because suppose I define any other uh, value, suppose x naught, that is not equal to a, then this f of x naught into delta of x minus a, what would this value be? If this x naught not be equal to a, then this f of x naught times delta of x minus a b. Can you write it in the chat?
Excuse me, sir. Can you please
Yeah.
increase the volume of your mic, sir?
Am I audible?
You're audible, but your voice is very low, sir.
Okay. Okay. Are you able to listen to me now? Hello?
Yes, sir. Yes, sir.
Okay, fine. So let me repeat then. Fine. So, okay. So what I was saying is this comes from the definition of delta function. Okay. That minus infinity to infinity delta of x dx is equal to 1. This is how delta function is defined, right? So we need not prove this one, right? Because this is the definition itself of this delta function. So the other property of this delta function is that minus infinity to infinity delta of x minus a f of x dx is f of a. Okay, so this, so regarding this, what I mentioned was delta of x minus a is 0 everywhere except x equal to a, right? We saw that here, right? Delta of t minus 1, or say x minus 1, was 0 everywhere except at x equal to 1. Similarly, in general, this delta of x minus a would be 0 everywhere except this x equal to a. Was I audible thus far?
Yes, sir.
Okay, fine. So as a consequence, the integrand, this integrand, sorry, wait, this one, this would be 0 everywhere, and the only contribution from f of x will be from x equal to a. Do you agree with me on this?
Yes, sir.
Okay, so the only contribution from this function f of x will be from x equal to a, right? So f of x, the only contribution that f of x is making is this f of a. So now my question is, what will be the value of this? If x naught is not equal to a, what would be the value of f of x naught times delta of x minus a? Okay, let me check the chat window. Yeah, somebody said 0 and that is the correct answer. Yeah, fine. So this is 0. And if this x naught is a, then the value of this is f of
F.
x naught, right? Yeah, and this x naught is a. That's how this uh, property is written, right? That this value of this integral minus infinity to infinity delta of x minus a f of x dx is f of a. Now coming to the other property, which is also one important property, that delta of ax is 1 by modulus of a delta of x. I want you all to attempt it. Attempt this property. I'll give you a minute or so and then we'll try to prove this one as well. I hope you all are able to access this chat window. Sure. Okay. Let me now prove this one. So the property that we are interested is delta of ax is, sorry, this. Yeah, delta of ax is 1 by modulus of a delta of x, right? This was this property. So what we can do is, this delta function makes sense when it is under an integral, right? So we'll put it under the integral and then see if we can prove this. This minus infinity to infinity delta of ax dx, right? Now what I can do is I can write this as limit L tends to infinity minus L to L delta of ax dx, right? I can write it like this. And then if I'm not audible, just let me know, right? I'm glad one of you spoke up. And now what we'll do is we'll put this ax as some other variable, say y, right? Now what will the limits now be? Earlier the variable of integration was x, right? Now if we change it to y using this substitution, this means that y is ax, right? So our x1 was minus L and x2 was L, right? This x1 was this and x2 was this, right? So now I need y1 and y2, right? Since I'm saying that I'll be using this substitution, right? So what would be the y1 and y2? It is straightforward, right? Can anyone write it in chat? Was my question clear?
Yes, sir. Yes, sir.
Okay. So y1 would be a times x1, right? Used
Well,
this one.
sir,
Yeah, mine's.
minus LA. It should.
Yeah, mine's AL because x1 is mine's L, right? Good. So it would be limit L remains same, right? L tends to infinity. These limits change. For this y1, it is a times x1, so it is minus AL, and y2, it is a times x2. So this is a times L, delta of ax is y, right? Did I miss something?
So difference. We have to differentiate both sides, sir.
Yeah, yeah, yeah.
Then we'll
So,
get the value of dy.
fine, fine, fine. Glad you could point that out. So y is equal to ax. So dy is a times dx, right?
Yes, sir.
So dx is 1 over a dy. So
Yes, sir.
if I, instead of dx, I can write 1 by a dy. So yeah, we can write that over here. Now, there are two cases, right? Case when this a is greater than 0 and the case when this a is less than 0, right? Because the limits now depend on this a, right? Earlier, this did not depend on a, but now since we have chosen the variable of integration such that these limits have a, right? So now uh, the value of this will depend on the sign of a. Now, when a is greater than 0, what will happen? When a is greater than 0, this minus infinity to infinity, I'm writing this one. Sorry, right? I'm writing this integral here. delta of ax dx. The value of this is equal to, I'll be applying the limits in this step. Okay, help me out. 1 by a integral of, when L tends to infinity, this minus AL should tend to, now we are assuming this A is greater than 0. Okay, has somebody written in chat? Okay, this was the previous one. Okay, let me formulate it again. I'm saying I'm putting the limit L tends to infinity, right? What should this mean? I should use a pen instead. What are these two values? Suppose this
So
is
both
x
of them will be, one will be minus infinity, one will be infinity
infinity,
plus.
right? The x1, this one will be minus infinity, and this one would be plus infinity. So minus infinity to infinity, delta of y dy. Now, uh, I'm sure you all are aware that we can change the variable of integration, right? I mean, this is same as writing minus infinity to infinity delta of x dx. Is everyone convinced? Okay. If not, just let me know. I'll address that out. Now, another case is when a is less than 0. In that case, this limit, what should this limit be when a is less than 0?
Plus infinity, sir.
Yeah, plus infinity. And the upper limit is minus infinity, right?
Yes, sir.
So minus infinity to infinity delta of ax dx is 1 over a. Okay, what I'll do is I'll absorb this minus sign, right? If I interchange the upper and lower limits, then I can take out a negative sign, right? I'll do that in this step. Minus infinity to minus infinity. Have I done anything wrong or am I right?
Sir, the signs on the infinity.
Signs on the infinity, but I just said that I'll be taking this negative sign out. Is it fine?
Sir, if you haven't taken that
Mhm.
negative sign out, the lower side will be plus infinity and the upper side will be minus infinity. Now you have taken that minus sign out, then the limit should upper limit should be plus infinity and lower will be minus infinity.
Correct. Minus infinity to infinity delta of x dx, right? So does this prove that delta of ax is 1 by modulus of a delta x? Right. Let's see what's happening. For when a is greater than 0, this a is positive, right? And when this a is less than 0, we are defining this as minus 1 by a, right? So minus a. And that is how we define a modulus function, right? If suppose I have modulus of x when x is greater than 0, yes, less than 0. When x is greater or equal to 0, this modulus of function is equal to, agreed? And when,
Yes.
yeah, and when this x is less than 0, this modulus of function is equal to
Minus
minus of
x.
x, right?
Sir, in the last line, when you change the variable from y to x, uh,
Yeah, should I
from,
explain that step?
sir, then, sir, when you change the variable, there will be a factor of a coming in, sir.
Okay, let me, okay, wait, I need to admit. I'll add a page to explain that. Okay, what I did in this step, it not working. Yeah, what I did in this step was this a of x was y, right?
Yes, sir.
Okay, okay, wait. Let me do one thing. Would you be convinced if I write it this way?
Yes, sir.
Is this and this same?
Sir, y was assumed to be ax, sir, and
Okay,
dx 1 by a into dy.
okay, I got what you are thinking. So you said we use this y is equal to ax. So why not use that substitution, right?
Yes, sir.
The thing is minus infinity. Okay, why minus infinity? This is in general. Are these same?
Yes, sir.
Okay. In this step, I was using a substitution, right? Y is equal to ax. And what uh, what I'm doing in this step is I'm just changing the variable of integration, right? It's valid in general. If I just change, see, if I had substituted, so the other way to answer your query is this y was a dummy variable throughout, right? Our actual problem didn't had this y, right? If
Yes, sir.
this is causing some, what should I say, trouble, what you can do is then, I mean, you can go through this. I'm sure you'll figure it out. This is simple. If uh, this and this are same, because what we essentially are doing is we are just changing the variable of integration. It could have been z, right? I don't have any issue. Or do one thing, keep it like this. We still proved it. Then don't even change it for this. Okay, sorry. Wait, now we are fine. We are fine. So I hope uh, this part was addressed. I'll still formulate a better solution and write it on this. Okay, should we move forward?
Yes.
Okay. So now that we have proved this one, I'll give you a problem. So the problem is minus infinity to infinity 5 of x plus 1 delta of 4x minus 2 dx. I hope I did not miss the brackets. Yeah, I guess it's fine. So can all of you attempt this problem and write in chat the answer? Okay, can it be 11? Well, I guess we need to see that. Let's see. So the way we can solve it is as follows. Yeah, we just saw this property, right? That you can replace this delta of x by this 1 by modulus of x delta x. I'll use this property first, right? Then modulus of 4 minus infinity to infinity by x plus 1 delta of x minus 2 dx. Everyone with me till now? Okay, we have two answers now of 11. Is this step clear?
Yes, sir.
Okay, so this is nothing but 1 over 4. We can treat this as the function f of x, right? And the value, we saw this property, right? If we have this case, delta of x minus a and a function of x, this delta function picks the value of the function at a, right? So this is f of a. What should this be? By that logic, this should be f of 2, right?
Yes, sir.
So let's do one thing, evaluate this at x equal to 2. So 5 times 2 is 10, 10 plus 1 is 11. I guess that is why we were seeing 11 in the chats. And that's it, right? The whole value of this integral is 11. So our answer is 11 by 4. So I guess some of you were missing out this factor. Is this clear? Especially Ankit and Neeraj. I hope so. Okay, that is fine. What I can do now is, let me see. Mm, okay, attempt this problem. Problem number 4. Integral 0 to 1 1 over 1 plus alpha square d alpha. Does this integral look familiar? 1 by 1 plus alpha square. Okay, Ankit is saying C, and that is a correct answer. Let's see how. Ankit, could you unmute yourself and let others know how you came
Uh,
about that answer?
we can do integration tan inverse x equals to
Yeah, and then under the limits 0 to 1, that evaluates to pi by 4. Good.
yes.
So let me just quickly go over what Ankit was saying. So value of this integral is, this is well-known integral, that integral 1 by 1 plus x square dx is tan inverse of x, right? There is a constant of integration for this indefinite integral, but you can ignore that because the problem asked is of a definite integral, right? Since we have this definite integration, what we can write is tan inverse of alpha, since the variable of integration is alpha in this case, and under the limits 0 to 1, this is pi by 4 minus 0. Or wait, why should I skip a step? Tan inverse of 1 minus tan inverse of 0. That is nothing but pi by 4 minus 0, and that is pi by 4. Everyone following?
Yes, sir.
Okay. So alternatively, what you could have done in this case, suppose you were not aware that we're not knowing this result, right? I did this uh, using this result, right? The other way you could have done this is realizing that 1 plus alpha square, right? Mm, square minus alpha. Okay, so if we use alpha equal to this tan of theta, right? I'm using now a different approach, right? If alpha is tan of theta, what would this 1 by 1 plus alpha square be? This would be 1 by 1 plus tan square theta. And what is 1 plus tan square theta?
Sec square theta.
Yeah, theta. And reciprocal of this sec square theta is cos square theta,
Yes.
right? And then integral of, wait. I'm still missing out something. Okay, now fine. So cos square theta, right? But this was my substitution, right? So this d alpha would be, what is the differentiation of tan theta? Okay, so differentiation of tan theta is secant square theta. Okay, I'm saying is differentiation of this tan theta is sec square theta, right? I used differential on both sides. If alpha is tan theta, then differential of alpha is sec square theta, differential of theta. So that is sec square theta d theta. Now for the limits 0 to 1, when alpha was 1, right? Okay, no, let's start with 0. When alpha was 0, talking about this case, when alpha was 0, what should theta be?
Sir, 0.
Yeah, so theta should be 0. And when this alpha is 1, what should theta be?
Sir, pi by 2. This is pi by 4. Pi by 4.
Pi by 4, yeah. But cos square theta and sec square theta are reciprocal of each other, right? I could have their product is 1. Do you agree? Cos square
Yes.
theta times sec square theta is 1.
Yes, sir.
0 to pi by 4, 1 d theta. That is nothing but it says theta limits 0 to pi by 4, and that is pi by 4, right? Both of these approaches are fine. We saw two ways how we can solve integrals. So what I would suggest for these problems is that you should be, see, this took some time, right? And it's not necessary that for other problems it would end up in such a simple form, right? So you should all I would say memorize those formulas, right? You should readily be able to uh, recall that this integral evaluates to tan inverse theta and the other results as well, right? For example, what is if this had been 1 by 1 minus 6 square theta? Suppose this, just as an example, right? You should recall all these results. Reason being, you'll be able to answer quickly. Okay, this is done. Okay, I can take this resistor problem first. Okay, now this is the question 5, right? I want you all to attempt it and let me know in the chat.
Sir, please zoom the question, sir.
Sorry.
Please zoom in, sir. It is not
Okay.
visible clearly. The second option, sir, lower than the smallest resistor.
Okay. That is the correct answer. Let's see why is it so. Okay, given this configuration, right? R1, R2, 1 by R equivalent is equal to 1 by R1 plus 1 by R2, right? The other way to write it, simple algebra, R1, R2 by R1 plus R2. I'm sure you all know this well familiar formula. Now what we need to prove is the relation of R equivalent and R1 and the relation of R equivalent and R2. How are these related? Is it equal to, less than, or greater than? Right? Now what we can do is we can write it in this form. R equivalent is R2 times R1 by R1 plus R2. Right? So this means R equivalent is equal to What can you say about this fraction? Since value of these resistance will be greater than 0, right? What we know is R1 is greater than 0, R2 is greater than 0. Then can you comment on this one?
Sir, its value will be lower than 1.
Yeah, the value will be lower than 1. So if the value will be lower than 1, then we can write the following relation, right? And equality when this R2 is 0, or no, wait, ah, let's comment on strict. Similarly, we can write this R equivalent as R1 times R2 by R1 plus R2. Again, this fraction is less than 1. So R equivalent, shit, is less than R1. R equivalent is less than R2. R equivalent is less than R1. So as one of you pointed out, I guess Neeraj pointed out, this is the correct answer, right? Now I want you all to determine the limit of the following function. I'll give you a minute and then start solving it myself.
Sir, please zoom in, sir.
Sorry, did you say something? I was not able to hear.
Sir, please zoom in.
Okay, zoom in. Fine. Okay, you can solve along and I'll also start solving it. And if you're done, you can write your answer in the chat. Fine. So presuming this x is greater than 0. Okay. Now we know about inter indeterminate forms. Okay, someone has joined the lobby. Fine, admit. Now we are aware about these indeterminate forms, right? For example, 0 by 0, infinity by infinity, 0 times infinity, infinity minus infinity, 0 power 0, 1 power infinity, and infinity power 0, right? Uh, idea is if using direct substitution, you get one of these forms, then you cannot readily use direct substitution, right? If I directly substitute x as 0, then I would get 0 power 0, right? This one. So I cannot readily use direct substitution in current form. But what I can do is following. I have this limit x tends to infinity x power x, right? I can write this as e to the power limit of x tends to infinity log of x power x. Is this fine? What I did was I used this one, this formula. Suppose I had, ignore this, y tends to some x naught, why should I even write a limit? See, if I have y, I can write that y as e to the power of log of y, right? Because essentially that is again y, because this one is to the base e, right? Natural log. So by definition, this is some exponent, right? This is some exponent which when raised to power e gives y. Do you all agree with me on this?
Yes, sir.
I guess that's straightforward, yeah. Okay, then what I used here is log of limit is limit of log. You can uh, give it a thought. Uh, it's pretty straightforward. Then this can be written as e power limit x tends to 0. This one can be written as x log x, right? This is log of a to the power b, that is b log a, that formula. If something is not obvious, you can just point me out. I'll help you out with that. So this can be written as e to the power limit x tends to 0 log of x by 1 over x, right? I wrote this x as 1 by 1 over x, right? This again is same as this y. So now I'll use L'Hopital's rule. I hope you would have gone through L'Hopital's rule in the week 1 lectures. So I'll be directly using that, right? Limit extends to 0. So the idea is limit of a fraction is limit of derivatives of the numerators and denominators, a fraction consisting of those, right? So log x, the differentiation of log x is 1 over x, right? And derivative of this 1 over x is minus 1 by x square. And this is nothing but e to the power limit of x tends to 0 minus 6, right? And that is e to the power 0, which is nothing but 1. Why I used substitution in this step and not in this step should be clear, right? In this step, it was in indeterminate form. And in this step, if I use a substitution, it's not in indeterminate form, right? That's why I can use the substitution in this step. Okay, let's move forward. So this option A is correct. Okay, before going through these, let me go through. I guess we are short of time. I would not be able to show you this, but yeah. See, we have Just a second. Okay. J times sine hyperbolic of x. What is the value of this one, right? The options are, I had this in my slides, but I don't know. Somehow this one got deleted. Sine of jx, cos of jx, j cos hyperbolic of x, j sine of x. Okay. Attempt it for a minute and I'll go over this question. As a brief recap, this sine hyperbolic of x by definition can be written in terms of exponentials as e power x minus, sorry, e power jx rather, minus e power minus jx whole divided by 2 times j. I'm sorry, I guess I messed up. Was showed it for sine of j. Okay, this definition is for sine of x, right? Sine hyperbolic of x is e power x minus e power minus x whole divided by 2. Okay, the way we can solve this is use this one. Now, if sine of x is e power jx minus e power minus jx by 2j, then sine of jx would be e to the power. Okay, I want you all to concentrate. Now, if x is j times x, then e power jx becomes, if x is jx, then this e power jx becomes
e to the power j square x.
j square x, and j square is,
Sir, minus 1.
yeah, so can I write it minus 6?
Yes.
Hmm. So I can write e power minus 6 minus e power, can I write e power x?
Yes, sir.
Fine. Whole divided by 2j. This you can write as e power minus 6 minus e power x whole divided by 2. Sorry, I interchanged the sign, right? Is it fine? This is e power x minus e power minus 6 whole divided by 2. What is this? Does this look,
Sin hx.
yeah, Sine hyperbolic of x. And what is 1 by j? Wait,
minus
I
j.
guess, huh, but did I miss out a sign in between?
Yes, sir. Yes, sir.
Should be minus 1 by j, right? Because I absorbed a minus sign, or I should say I took out a minus sign here, right? That's why I was able to write this e power x and e power minus x. So this then can be written as j, right? Because 1 by j is minus j. So minus j times minus 1 is j. So this is the result that we got. Sine of jx is j times hyperbolic of x. So which option is correct?
First one, sir.
Yeah, the first one. Okay, and after this, I have one more problem on these hyperbolic and circular functions. Someone is waiting in the lobby. Okay, the other problem that I want you all to try for a minute and then I'll solve it is this one. Uh, Problem number. Okay, what is the value of this cos hyperbolic of x? Right, cos x. And your options will be uh, cos x, cos of jx, sin x, sin of jx. Right, give it a try. Okay. What is the value of this cos hyperbolic of x? And your options are these four. Let me start solving it as well. Now, by definition, this cos of x is e power jx plus e power minus jx whole divided by 2, right? And yeah, what is cos hyperbolic of x? I hope you are aware of the definitions, right? This was
Yes,
taught in week 1, right?
yes, sir.
Okay,
E to the power x plus e to the power minus x by 2.
yeah. Now, as we proceeded in the first problem, we evaluated sine of jx. Let's evaluate cos of x here. Sorry, cos of jx. Cos of jx is e power. Again, you'll need to concentrate. E power jx. Now, if I use uh, jx instead of x, then there would be one more j here, right? And j square is minus 1, so it would be e power minus 6. That's why I'm writing e power minus 6. Fine. Plus e power x. I hope it's clear.
Yes,
You
sir.
can interrupt me if you have any doubt. E power minus 6 plus e power x divided by 2. And what is this? Does this look
Yes, sir. Cos hx.
so? What should be the answer? B, right? Should be B. Yeah. Okay, let me see what else. I showed you this one. Okay. Now the problem is this one, right? Problem number 7. Uh, Give it an attempt. U of t times delta of 3t. A hint, what is delta of 3t? We saw one property. This is nothing but 1 over 3 delta of t, right?
Sir, option 2, sir.
Option number 2, 0.33 u of t, correct answer. So now u of t times delta of 3t is u of t times 1 over 3 delta of t, right? And that is nothing but 0.33. Oh, wait. Should be delta of t, right? I guess option 3, u of t times delta of t. Let's see why that is so. This is u of t, right?
Yes, sir.
And delta of t is, I'll be overlapping this one. See, delta of t is this, right? This is my delta of t, and this is u of t. Stopping. Now, when you take product of these two functions, delta of t is 0 throughout this region, right? It's 0 throughout this region. Can you now see why delta of t times u of t is equal to delta of t, right? In other words, what will this product be? This product will be nothing but a delta t, right? If I take a product of these two functions. And in our case, there is a factor of this 0.33. So what will happen is, see, this 0.33 was this 1 by 3. Effectively, we'll have a delta function 1 by third the magnitude, right? If this is 1, I'll have a delta function somewhere here. Delta. See if this is actually delta of 3t, right? Which I wrote as 1 by 3 delta. Is it clear? If not, I'll repeat it.
Yes, sir.
Okay. So that is problem number 7. Now coming to problem number 8. The conservation of energy and charge are best represented using dash and dash respectively.
Sir, conservation of energy is represented by KVL, and
Mhm.
conservation of charge is represented by KCL.
So the correct answer is option A, right?
Yes, sir.
Yeah, Ankit also mentioned that in chat window. So let me just briefly go over this. This KVL law can be viewed as conservation of energy. Reason being, see, what is the statement of KVL? KVL states that the total sum of all the voltage change in the closed loop circuit is equal to zero, right? If I'm having a circuit, a closed loop circuit, the voltage change should be zero, right? I'll represent the voltage change by delta V. And this is consistent with the conservation of energy, right? As it implies, in other words, that the energy supplied by the voltage source is equal to the energy consumed in the circuit, right? You can say that KVL, in essence, the manifestation of this conservation of energy in electrical circuits. Now, similarly, uh, the KCL states that the currents that go into the node and out of the node are equal to zero, and we can view this from uh, conservation of charge angle as well. See, uh, conservation of charge states that if uh, any charge enters a node, if any charge enters a node, suppose we have this node, right? Same amount of charge should exit that as well. Okay, you can think of KCL in terms of water analogy as well. See, water like charge cannot be accumulated at a point in a pipe, right? Suppose I'm having a pipe, right? Water goes in, water goes out, right? It does not accumulate on its own. That is a rough analogy of uh, KCL, or this conservation of charge. And in fact, these conservation of charge and conservation of energy are more fundamental than your KVL and KCL. And as we made a statement in case of KVL, we can make a same statement for KCL as well, that KCL is the manifestation of conservation of charge in electrical circuits, right? Now with that, let's go through the last question of today's session, the derivative of g of alpha, where g of alpha is given by this function. It is straightforward and I expect you all to solve it. Are you all able to access the chat window? Can you at least write yes? I'm sure about Neeraj and Ankit, but other people? Okay, fine. Okay, let me now start attempting it myself. Now, g of alpha is 10, alpha raised power 5 by 2. Okay, option D. Ankit says option D. Let's see how it goes. 10 times alpha raised power 5 by 2 minus alpha. Okay, this is alpha raised to power 8 and square root of that. I can write it as alpha 8 by 2, and that is nothing but 4, right? Alpha raised to power 4 plus 6 times alpha raised to power 2 by 3, right? And now, wait, stops working sometimes, I'm not sure. Now, derivative of this function g of alpha is 10 times this 5 by 2 alpha raised power 5 by 2 minus 1, right? This 5 by 2 minus 1 is 5 minus 2 by 2. That is nothing but 3 by 2, right? Minus alpha raised power 4 plus 6 times by 3 alpha raised power again 2 by 3 minus 1 is it's minus 1 by 3. So do we have answer? This is wait, yes, I flipped it up, right? Should have been 2 over 5. Yeah, rest of the things are fine. So this would be over 5 and exponent will be over 5 minus 1, which is minus 3 by 5. So the right, this is 2 times 2 is 4. Okay, I forgot to take a derivative of this term as well. 4 times alpha raised power 4 minus 1 is 3. Is it clear up to this point? Or should I repeat it?
No, sir. Please continue.
Okay. So this is alpha raised power minus 3 by 5 minus alpha cube plus P1R, 32R, P1R, 32R, 2 2s are 4 times alpha raised power minus 1 by 3. Right, I can take that 4, see 4 occurs here, here, and here. So I took that out.
Okay, sir.
Is it fine? So the correct answer is now, I guess option B, right? Minus 3 by 5 minus alpha cube plus, yeah. Okay, now what can I do? Let me now. Okay, do you have any question first? I just have one animation for this circular trigonometric functions and hyperbolic trigonometric functions that I'll show at the end. But before that, do you have any questions with regards to the problems that we discussed today or any doubts? And I hope I was audible.
Yes, sir, we can hear you. Sir, I have one question that, sir, which sections of mathematics are important for signals and system,
For
sir?
signal and systems, uh, I would say all of these sections are important. See, you'll be using these trigonometric functions uh, ahead in the course, right? Uh, as you'll move ahead in the course, you'll be using functions. Signal and systems, what is signal by definition? It is a function, right?
Okay,
So
sir.
the functions that you learned are, for example, trigonometric functions, the hyperbolic trigonometric functions, cos, sine, cos hyperbolic, sine hyperbolic, and after that, uh, being comfortable in expressing the complex exponential as, you know, complex exponential in the form of trigonometric functions. You should be comfortable in these. Also, derivatives, that is also important. And after that, I guess, yeah, these unit step, unit ramp, delta functions, these are also very important. All of these are important.
Sir, probability and linear algebra, they are no use for this
Probability and
subject.
linear algebra, no, I don't think so. For this course, no. You should be, your calculus should be strong. I can say that. Your
Okay,
calculus should be strong. Calculus should be strong. You should be very much comfortable with differentiation, integration, and maths. But if the question is, do we need linear algebra? Then no, probably not. You don't need linear algebra in this course.
okay, sir. Thank you, sir.
Okay. Yeah, let me now show you an animation first. Just give me a second. Just a second. Okay, the file is loading. Let it load. Meanwhile, okay, let me share this tab. How can I share? Okay. Are you able to see this?
Sir, no, sir. Your screen is blank, sir.
Okay, wait. Now?
Yes, sir.
Okay. So in the beginning of the lecture, I mentioned that these circular trigonometric functions and hyperbolic trigonometric functions can be defined using the circle and hyperbola. This is basically the illustration of that. See the theta. Are you able to recall this as equation of circle x square plus y square equal to 1?
Yes, sir.
Okay, so and x equal to cos theta and y equal to sine theta will satisfy it, right? And as you move theta, notice how this point traces this entire circle. For theta 0, say for a theta equal to 30, I can keep it as 0 as well. This goes to 0 and then 45 should come where somewhere around here. So the idea is as you increase the value of theta, this cos theta and sine theta, they trace out this unit circle, right? And similarly, for hyperbolic functions, if we change the value of this t, the argument of hyperbolic functions, this traces out the unit hyperbola. For example, let me use, it is probably too large. Is it clear? I mean, this was just for illustration purpose. This is also how we can define these trigonometric and hyperbolic functions in terms of equations of this unit circle and unit hyperbola. So let me stop this and wait. Okay, let me know, are you able to see this? Are you able to
Yes,
see?
sir. Yes, sir. Calendar.
No, no, I did not meant calendar. Better switch back to the iPad. Probably I think it won't let me. Just a second. Hello. I'll be taking your 10 minutes. Okay, so this part is optional. Now, uh, I'm sure we are aware of this Euler's formula, e power jx is equal to cos x plus j sin x. Now, I'll show you. Let's look at the proof of the same, right? So, effectively, what I need to prove is, say, if I have a complex number z as cos theta plus j sin theta, I need to prove that this z is nothing but e power j theta to prove this, right? Now, if I take a derivative, this is j times, oh, okay, so what I was saying is z is cos theta plus j sin theta. I need to prove this Euler's formula, and for that I need to prove that z is e power j theta, right? I can take a derivative dz by d theta, that is, wait, what is derivative of cos theta?
Sin theta, sir.
Yeah, it's actually minus sin theta, right?
Okay, sir.
And derivative of sin theta is cos theta, right? So dz by d theta is j cos theta. Okay, I can even write plus as well, j square sin theta. Can I write it like this, right?
Yes, sir. Yes, sir.
So this is j times cos theta plus j sin theta, right? This is nothing but jz. So dz by d theta is j times z.
Okay, sir.
Then this gives me dz by z is j times d theta. If I integrate on both sides, I'll get ln of this z. This is natural logarithm, j times theta plus c. This is, now if I take exponential on both sides, I can write e power ln of z, right? E power ln of z, but e power ln of z is z. I hope you are
Yes.
able to follow. And e power j theta e power c, because e power j theta plus c can be split into two exponentials. So this is nothing but a constant, right? So I can write, let this be c1, the constant of integration is c1 and this c. Now z is c times e power j theta, right? Now what can we make comment about this c? What if we use theta equal to 0? That would give us, right?
Yes, sir.
So z is 1 plus j0, that is 1, right? If we use theta equal to 0 in 1. Now from this, if I use theta equal to 0, what I get? That is c, right? Because e power j times 0 is e power 0, that is 1. Z equals to c. From first I got z equal to 1. So I can conclude that this c is 1, right? This then becomes e power j theta, right? That is what I had to prove, right? Also, one last proof and then that's all from my side. Show a last. So we just proved Euler's formula, right? E power jx is cos of x plus j sine x. And if I use the minus x instead of x, then it is cos of minus x. Cos is an even function, so it will be x. Sine is an odd function, so there would be a minus sign coming out. If it's not clear, you can let me know. I'll address it out. Now I have these two equations, right? And I'm interested in getting an expression of cos as a function of for jx e power minus jx, because that is what we used in this session as well, right? I'm effectively trying to prove that expression. Sine of x is I'm interested in obtaining a function, right? What if I add a and b? If I add a and b, then this adds up, right? What about this? They will cancel.
Yes, sir.
So a plus b would give me,
2 cos theta.
yeah, 2 cos theta. And what is a plus b on the left hand side? That is e power jx plus e power minus jx, right?
Yes, sir.
So cos of theta is this. That is what we used in this session before, right? This is just a proof of how it comes about. Now, what if I take a subtraction a minus b?
So cos x will be cancelled.
Yeah, it will cancel. And what about this minus sign?
It will
This will be
change.
plus, right? So this will add up.
Yes, sir. 2j sin
And
x.
2j sin x. And a minus b on the left hand side is e power jx minus e power minus jx. That is this 2j sin x, right? I'll bring this 2j in the denominator, right?
Okay, sir.
Yeah, then there are some identities of these cos hyperbolic functions that you can have a look. I'll update the slides. You'll get access to these slides as well, and I'll reframe the solutions and put up the identities and material in a proper form. You can have a look at that as well. Okay. And any question?
No, sir.
Okay. And any feedback you would like to provide? That was all from my side. Uh, thank you.
Okay, sir.
That
Thank you,
ends
sir.
the meeting. Thank you.